So we're going to do a problem, then a multiple choice problem, then a multiple choice, and so on and so forth. We'll talk about what you need tomorrow morning and timing and all that stuff as we get there. So, review session number 5, final one. There is no 6. Okay, here we go, right away. A pure 14.85 gram sample of a weak base is dissolved in enough distilled water to make 500 mils. A, calculate the molar concentration of C2H5NH2 in the solution. So let's do that first. So we need to find the molarity of that. Should be able to do that fairly simply. I will tell you that's worth 2 points. Please, give it a shot. At least get the setup going. Again, calculators always for this stuff. No, whenever it says question 1, give you extra confidence. Like, okay, this is one that's probably going to be showing up. I don't care what year it is. It's things that'll probably be there in the first 3 questions. As always, if you hear me writing, don't look up if you're actually working on it. For certain things, I want to get ahead of you because it's just one of those, when you're done, did you get it? Other things, I don't want to even give you any tips because I want you to see what you have to say about it. 2 points, 1 for solving for moles when you get it, 1 for the actual molarity. Don't ever feel like something's too easy. It's all good. Things are going to be more difficult for some people, more straightforward and easy for others. Please go with it. Letter B, as we finish that up. And again, at any time, ask a question if you don't understand where a number comes from. Don't be too worried. I rounded that. If you're using more specific numbers, that's great for the molar mass. Write the equilibrium constant expression. Okay, should be able to do that. I want the equilibrium constant expression. Can you, I don't know if it'd be right or not, can you give me the correct K? Don't say it out loud, please. So what subscript would the K have? Think about what's all been said so far. Remember again, you have K, technically KEXP is like the KQ for the equation. You have KAs, we have KBs, we have KWs, we have KCs, we have KPs, we have KSPs. A lot of Ks. Nolan, what is a K? C. Oh, so close. B. Nolan, what happened to your voice? It's so low. Weak base. Hey, KC is a good miss. At least it's brackets, right? KP would be the furthest away from that, because then you really didn't write it right. But there we go. 1 point. You either did or didn't. I'm not going to write the points every single time. I'll just show you when there's more than one for that. So, right. Remember, always, equilibrium constant expressions. It's not looking for values. It's just, can you put them in the proper relationships? Always leave out liquids. Always leave out solids. Of the two in the equation, which is present in the solution at higher concentrations at equilibrium. Justify your answer. There are no values. So anybody want to just talk to me about this? It doesn't say calculate. So this is an interpretation kind of question. Anybody want to interpret this? So basically, this, let's make sure we understand this. It's saying, is this or is that in higher concentrations, correct? That's what it's saying. Anybody want to, this isn't a big leap. The minute we give the answer, you're like, oh, yeah, I guess that would make sense. Which one would be present in a higher concentration? Let's just call it H2 or H3 if you like.
Because it's a weak base.
Yes. So because it's weak bases, it doesn't move as far to the right, period. It's a strong base, it goes further to the right. Strong anything goes to the right, weak does not. So perfect, and that's what you just say. Okay, that the weak, because it's a weak base, you will have more reactants, or the actual base does not dissociate, if you're looking for a specific term. I will read what they have to say. The C2H5NH2 is present in solution at higher concentration in equilibrium. The weak base, it's a weak base and thus has a small Kb, therefore it only dissociates partially. Okay, so this will be much higher concentration. This is how I would write it. That's what I would say. That's one point. So, please, take a breath. If you're like, whoa, they didn't give me any numbers. Obviously, if they gave you a K, and a K is less than 1, that means you have more reactants than products. Then that would tell you. But the fact that it's a weak anything, it's always small. That's the whole reason. That's why strongs don't have Ks. Because we know that it just goes all the way to the right. Okay? So, obviously, if you have two different Ks, the larger K means that more of that one goes to the right. It still goes to the right. It's not a lot. Okay, D. A different solution is made by mixing 500 mils of 0.5 molar ethylamine with 500 mils of 0.2 molar HCl. Assume that the volumes are additive, meaning that now you have those two volumes together. The pH of the resulting solution is found to be 10.93. I. Calculate the concentration of OH in the solution. What? Okay. Do I need an ice box? No, Mason, what? You were ready with that. What do you have to do?
You just find the pOH and then do
The equation.
Yeah.
Okay, but we'll get to the. You're right. A little hazy on the details, but remember, pH is a final idea. pH is at equilibrium. pH is meaning that the solution has already reached wherever it's trying to go. We're collecting data on it. So pH, there are two ways you could do this. There really are. I mean, you could find, if you take 10 to the negative that, what's that? That's H plus, correct? How do you get from H plus? Just remind me, how do you get from H plus or OH minus if you're in H plus? So KW over, all right, KW over that. So it's confusing because KW can equal Ka times Kb, but then also H plus and OH minus relate with KW as well. So you could have done it this way. I would have done it how Mason would have done as well, though. Let's get into POH, right? Then take 10 to the negative POH, and that will equal my OH minus. Again, just take a breath. Remember, anytime I'm doing an acid or base, there's always a longer route and a shorter route, and I just have to take a breath. Remember, please, that pHs and POHs and H pluses and OH minuses, I saw a lot of people make a mistake. I don't remember which problem it was anymore, but you went right into it, and I believe it was actually something similar to this. We need an OH, and you just use that value. You can't do that. Okay? So, you do all that, you show your work. It should have been, all you have to do is plug in the numbers that I just had there. And that's just 1 point. Another hint of that is that because of the fact that that's a single I, and it's the first one, it's probably not full on yet. It's not just like, here you go, let's go, big, huge ice box. I haven't looked at the next two yet. I think there's two. I'm going to guess we're going to probably start to use these values now in an equation. My best guess, probably the first one is what is going to be an initial pH or something like that, and then what if I add something else, kind of like a buffer. All right, let's see what it is. Oh, not yet, sorry. Just an equation. Write the net ionic equation that represents the reaction that occurs when that solution is mixed with HCl. I don't want to show you at all. Please do this. This is a struggle that we continually have, writing equations. So, please, if you're stuck, write what you know has to be in there. Ask what else has to react or what has to be made. There are certain parts, I know this was made, or I know this has to react, and go from there. Okay? If you don't have it, if you already have it, you can look at the next one if you like, or you can just relax. two answers you could give. Net ionic. Whenever you say net ionic, strongs only bring one thing to the table. If it's NaOH, I'm writing OH minus. If it's an HCl, an HNO3, strong anything, I'm writing H plus. Or I'm writing H3O plus. What's the difference? Let's talk about that. So in this case, if I have this, what is created? If I have that, what is created? Now, if you're like, well, I don't know. I don't know if I can even do anything with this one. If you're doing the H plus, you're basically omitting water. Water's just not going to exist. Like we assume it's just happening in there. So this side will look literally like this, which I think feels a little weirder because you're not tracking acids and bases. This one's a little more substantial. Why? It's the same idea. But then I just have that. Or H2O if you want to write it that way. Either way, what happens, remember, keep it straight. This is a base. The base has to gain the H, right? It has to gain an H. It has to gain an H. There it is. So, as long as you can keep that straight, you're good to go. What's confusing is if you ever see it like that, you're like, whoa, wait, what's that now? That stems off of my strong acid still. It's one point, one way or the other. But those always just seem to be kind of tricky. Like, well, where's the OH and the H plus? You don't get OH or H plus when you add a strong. You're just driving it and making the conjugate partner of that thing in the beginning. Okay. I'm going to guess there's some points waiting for us, though, at the end. The last one usually is more difficult of a triple. Not always, but calculate the molar concentration of C2H5NH3 plus that is formed in the reaction. Okay, so I got to go back up to letter D. Any suggestions of what I should do? Ice box. I'm assuming those are sunflower seeds that were?
Yeah.
Okay. Just checking. I don't want to dip into your grades or anything, but. Can I use this equation?
Sure.
I have to. I have this and I have that. Just remember, you're taking your two reactants. Sure. I don't even know why I'm writing it. I have it right above me, so I'll just leave it. So, I need to get into moles. So I'd like you to give it a shot, check it out with each other. All you need is the molarity, the molar concentration that is formed. So what is that? I want the molar concentration of that, right? When I'm done, it's basically what it is. So continually think about that. Molar concentration, moles over liters. Think about what needs to be done. You have to consume, though. You're adding acids and bases together, so something's going to get consumed. In a problem like this, I guarantee probably acid is running out. Otherwise, you wouldn't care about the other thing because you'd have acid left over. So that would be more important than any conjugate acid. This is a weak conjugate acid compared to a strong acid. I'm going to do a little bit of work to see where we were at on this. You didn't do exactly the way I did it. It's probably okay, but. If you're not sure if you can do millimoles or not, then I wouldn't do it. But if all you're doing is millimoles works is if at the ending of it, you're going to redivide by a new volume. And you're just going to redivide by milliliters. Then millimoles are great. Because then I don't even have to move any decimals. I reduce potentials for human error. At least that's how I look at it. Max, what am I going to write in my change? Perfect, right? You got it the least amount. Good. And because of that, on the right, it's plus 100. Which is all that I care about, by the way. I'm not actually going to keep going. I'm recognizing what I need. right? It's not asking for pH at the end, which I will talk about, just to add to it. But I have 100 millimoles. Let's get this out of here. Jordan, what should I put that over? Yep. No, they changed what we were using. It'll be 1,000. Yeah, and that, of all the things I ever make a mistake on, it's the new volume sometimes. You got to make sure. So, and be careful if you're doing millimoles. Make sure you're doing milliliters. It's a big deal. Big deal. So math is not the tricky part here, and we're done. What if I ask for the pH, and we want to, in 1 or 2 sentences only, what could I just do basically? I want the pH of this solution right now. What could you do? I'm not quite there. I need to calculate a few more things, but I'm really close. So the Henderson Hasselbalch, what would I need? I need this number and the molarity of this one, right? So it'd be 150 over 1,000, right? So it'd be 0.15 and 0.1, and I take negative log, but I don't have a Ka and all that stuff, or Kb, but that's where you could go with it. Remember, if it's POH, if you have a Kb, POH equals Kb plus log, what is it? Acid over base. At the bottom one's always how it's related. So if I'm doing pH, it's acid on the bottom. If I'm doing POH, it's base on the bottom. It's the only equation you probably need to have memorized. Everything else will be on your sheet, which you will not rip out. Or Mr. Anderson has to write individual requests to make your test valid. So, oh, I'm sorry. There's one more. I was on a different page. Watch. Is that asking for pH? Oh, hold on. That's 2 points though. 1 point is earned. Oh wow, that's not bad. 1 point is earned for how many moles that you ended with. I think I'm reading that right. No, not. 1 mole is for this, right there. Just taking moles times volume, molarity times volume, and then 1 point for the final one. Always good to see when there's multiple points. Okay. Calculate the Kb. Calculate the Kb. Well, the Kb has to be, what does that mean? I need to know, oops, all right. I need to know everything at the ending of my equation. Well, what equation? It's at the, a Kb has to reflect the dissociation of a weak acid or weak base. This is not a dissociation. This is just it getting driven to the right. You know what I'm saying? Like a Ka or Kb has to have H plus or OH minus on the right side. Okay. So we need something a little different, just a little bit. I think we wrote it down earlier, else it was given to us. There it is. There she is. I need that. I need to utilize that. So I'm going to just use these values. Okay. Let me just reread, make sure that I'm looking at this right. So instead of it saying what is the pH, it's asking for what is the Kb. So I'm going to just rewrite this so we can see it. We're almost done. I just want to scroll up and down. What is happening? So there's a couple things we know, and it's asking right now, like, what is the Kb? Well, we can figure out based on relationships all the time. This is how much at this exact moment we have of this. If we had finished this problem, we would have had this. Where am I? 125. That's it. Did you say math?
That was not me. That was me.
Should we just pen, marker, whiteboard,
Dummy.
blue writing, red writing?
Guns, colon.
Holy cow. So where's the OH? We solved for it earlier, didn't we?
Yeah.
When it's I, double I, triple I, 4, 1D, it's all related. So it's all part of that same situation. Was it like 8.4, 8.5 times 10 to the negative 4? Okay, so take a moment and go, wait a minute. Do I have all these items? It's not asking you to start over. So I guess I went back up to show you that's the equation I need, because you can't just all of a sudden use this one, because that's not related to the dissociation of an acid or a base. But if it's in terms of a I, double I, triple I kind of problem, slow down, think about the things that you've done. They are purposely building you up. They are trying to get you to solve for different things that you can apply later. 1 point is earned. Check this out, by the way. 1 point is earned is if you did get this value from here. So they could have followed this up with saying, what is the pH right now? But the thing is, they already told you the pH, I believe, in the beginning. I mean, that's the whole point. They told you what the pH was going to be. So then that's the value, and then you just plug it all in. So 1 point is for the final answer, which is 5.67 times 10 to the negative 4. That's math. Okay, calculators away. Just flip them upside down or whatever else. We are going to mix this up a little bit to keep this a little fresher. Okay? So what I'm wanting you to do is we are going to do just 6 problems. So just do the left side. Please don't go ahead. I'm going to give you 6 minutes. If you feel, I'm not going to yell stop really loud. Technically, you have about 1.5 minutes of problem. Technically. No, I'm not. But if we can do this in 1 minute per problem, then we know that we can have extra time on the test tomorrow. Oh my God, I can't believe I just said tomorrow. Hold on. No. So, write all over it, please. If you have to do calculations, write them on the side. Don't waste your time on units and things like that. You're just doing the 6 on the left. Do the best you can. Okay, when you're done, you're done. I'm going to put the time up here, though. We understand no calculator? We're just doing up through number 26. Okay? All right, give it a shot. You got 6 minutes. Be serious about it. Good luck. Go. 1 minute. Okay, for the most part, I'm also trying to show you that a lot of these things are time savers. Like most of you were done earlier, you're just double checking things. These are the ones, if there's no math, some of them are really quick. They take you 20 seconds. You're buying time for the ones that are going to take you longer. So let's quick go through this because we're going to do a bunch of these tonight. Triple point is letter C. It's where you have a gas, liquid, and a solid. All at once. Just crazy to think about. And that's with pressure and temperature, by the way. Number 22, see if you get this one right. So here's the big hint to you, by the way. If you're asking about a certain element, then that's not the one that you potentially know, quote unquote. You have to know the other thing. So you know that hydrogen is +1, and there's 2 of them, so that would be a total +2. So that means that this has to be a -2, so this has to be -1. And you're like, wait, what? That is peroxide. That is an polyatomic ion, technically. It is not a normal oxygen atom. It's the one exception to oxygen. Okay? So that's why it's actually -1, but I'm trying to show you how you could have figured that out. You always go after the one that you are not being asked about. 23, a little math, potentially. So if you have a liter forming, so all this, it's telling you, believe me, they know you don't have a calculator. So, and they can give you a formula. So if you have 0.5 molar solution, how many moles of glucose are in 500 mil, sorry, if you have 1 liter forming 0.5 molar, how many moles are in 500? So what I did is this. I did, if it's this versus now it's this. That's how I did that. So, oh, there it is. It'd be half. You cut the volume in half, so you have half the moles. It's still the same molar, like you want to still make the same molar solution. So that's how I did that one. I'm still making the same, I didn't say I'm making a new molarity. Okay? What's density? Density is mass over volume. That whole paragraph, after everything's said and done, it's like, oh, what else do you need for density? Well, I have volume, so I need mass. It's mass over density. 25, describe which of the following statements best describes the effect of temperature on reaction rates. Reaction rates decrease. No, they don't. Only rates of reactions involving molecules with low energy bonds are dependent on temperature. Everything's dependent on temperature. If it's an absolute kind of like always or never, be very careful about those. And rates of reactions involving catalysts are not dependent on temperature. That has catalyst and temperature speeds it up, but it's still dependent on temperature. So that's the only one. I mean, every reaction, sneeze, paper, math, nauseous. Here's an equation. Catalyst decomposition follows the rate law of that. What is the overall order of this reaction? What is that? What's the overall order of that? Why is it second? You add these two, right? It's not because of that. If it says it follows a rate law, let's go, molecularity, it's second order. If there were 3 compounds, it'd be third order. If there was 1, it'd be second or first. Wow. If they give you the rate law and they say it follows this rate law, especially if it doesn't correspond to an actual equation, then that's the slowest step. So there you go. Hopefully you did well. And we're going to move on. We're going to do a lot of multiple choice today. All right, let's get to the next problem. This one's going to go a little faster than the first one because it's not a first problem, it's a 6. Okay, in the box provided, draw a complete Lewis electron dot diagram of IF3 molecule. Someone had to do this on final. So, try it first, and then I'm going to give you 2 big hints that you need to think about. So I need the electron dot diagram. So you can do bonds, okay? So you can draw it right in the box or do it on your sheet, whatever you're doing. You can do bonds, but you need to put dots on everything else that's not part of the bond. I guess I'll say this. What do you always assume about all the bonds in any molecule in the beginning? They're all single bonds. Make everything bond once, okay? That's where I start. So I'll get us started if you're like, I don't know what to do. Anybody want to interpret this for me? Does shape matter in this? Like, do I have to worry about the geometry of the actual 3D or no? Lewis electron dot diagram has nothing to do with the actual exact locations of bonds. Okay? I assume everything has an octet. If you want to make sure you get this right, there's 2 rules you just have to do. Make sure everything is bonded, make sure everything has an octet. And then what you need, and a lot of you will bypass this, you need to add these up. This is 7 times 3, right? Because the second last column is 7 valence electrons. So I got 21 here, and I got another 7, right? I should have 28 electrons. That's really important. How many do I have right now? I have 26. So I need to, and I add it in the middle. That's how you do it. Give everything an octet, bond everything once, then add it up. If that equals 26, I'm done. I mean, if it's the same amount of numbers. Oh, that was 28. Shoot, I'm short. My picture is not enough. In this case, it was only 1 point. Sometimes you get 2, depending on what's all happening. On the basis of the electron dot diagram that you drew, predict the molecular geometry of IF3. That would be...
What's the name of the model for a different 3D instead of the sky?
I think you would just say draw the molecular geometry. I've never actually seen on a test where you actually have to draw it like you know. That would be the first time. What is the shape though? Talking about the geometry. Do you remember? It is. It's a T shape. If you can't remember this, guys, 5 is a trigonal bi-pyramidal. I'm just going to show it to you. We put lone pairs on the triangle. I don't know why I'm drawing this up here when the question's below us, but. So this is T-shaped. Consistent with whatever you drew above. So if you did not put both lone pairs in the middle, you would have said this was. If you only put 1 lone pair in the middle? Gosh, no. What? No? Trigonal pyramidal. Seth, winner. Dinner of chicken. Please understand, almost every shape I've ever seen, it's 1 or none. So it's not like, oh my gosh, I can't remember that one. I can't remember square pyramidal. It's a point. Do the best you can and move on. Okay. I'll tell you this. If the following question asks for the shape of what you drew, on the basis of the electron dot diagram, it literally says that you drew. If you don't feel good about what you drew, and then you're like, I don't know the name of what I drew, go back up and change it to something you know, like a tetrahedron. I'm not kidding. A tetrahedral or whatever else. You lose the point for the first part, you'll get it for the second. Otherwise, you're like, I don't even think I did the first part right, and now I'm going to botch the second part and call it a trigonal cantaloupe or something like that, and I'm done. I've lost 2. So think about that. And I'm not trying to, don't manipulate your test like an English paper where it's like, okay, if I tweak the margin and I find the font that makes the space bigger and I add 2 pages, don't start doing all that. But okay. In the SO2 molecule, both of the bonds between sulfur and atom have the same length. Explain this observation supporting your explanation by drawing it in the box below a Lewis dot diagram. Okay. Curious if you can get this right. So use the same idea that I just did. First off, you need to figure out what the heck it even looks like. Okay, so they've established we're working on Lewis dot diagrams and things like that. It's saying that the bond length is exactly the same between the both of them. But why? Why? Well, why? I'm just going to make a Lewis dot diagram first and see what's up. So let's just narrate this a little bit. What's wrong with my diagram right now? I have too many, right? I have 20? I only have 18. Oh, you have too many. Your first instinct, put more on. No. So I either add dots or I have to add bond. If I add one bond, be smart. You got to take something away. Is that now 18? It's got to be the same number of electrons, but octets everywhere. So I have octet, octet, octet. So if you did not get that far, now it's trying to show, you got to show a picture. It's not giving anything away here. So I'm seeing if you understand what you're supposed to be doing. What should this, what picture should you draw to illustrate that both bonds, meaning the bond length here is the same as here? And if you don't understand it at the ending of this, you will, and it's a good question to go over. What shape would this be, by the way? It would be a bent. It's a trigonal planar bent. It's a bent, though. So it'd have like a less than 120 degree, because the lone pair would push down a little harder. So anybody feel like maybe they got this? Like what they drew? Doug? Aha, you could do that. So what are you saying? Like kind of like that? I think you get away with it. What's another way? What if I drew two of them? That's my hint.
Oh, the resonance structure.
Yeah, what if I drew that? Now, if it's not bent, I don't think it's a problem. If you drew this, what I'm saying, and assume there's dots on there, please. But what am I saying? I'm saying half the time it looks like the one on the left, other half the time it looks like the one on the right. So the bonds are basically 1.5 bonds at any moment. That's what it means. That's how you need to interpret this problem. So 1 point is earned for the correct diagram. Can be done with dots or lines, so you wouldn't need to have all the dots. Now, I don't know if you actually have to make it bent. It did not say geometry. So if you just had it straight like this above, probably be fine. So 1 point though, if you found out it had a double bond, you get a point. That's not bad. And then 1 point is earned for some indication or discussion of resonance, but the point is not earned for a description of resonance as a dynamic process. So don't worry about it.
Need to explain this or not?
No, if you showed it like this, you might want to just say it's a resonance structure, so the double bond moves from one side to the other. I mean, if you felt like you're like, I know this, I'm not leaving this problem without at least saying something. But let me just look back at how it explain this observation, supporting your explanation by drawing. So you should probably have a sentence, because it says explain this observation, supporting your explanation by drawing in the box below a Lewis electron dot diagram. You need to have something to say.
What are the two
Kobe.
elements that only need 6?
Good question. B and AL. So B and AL have a ball, have a Lonzo ball. You'll have, because it only can make 3. Okay. So it can't have an octet. Guys, what's the hybridization on either one of those? SP2. Why? 1, 2, 3. SPP, right? So that's letter D. 1 point. Finishing up, I believe. Last time I thought I was done and I wasn't. And no, I'm not. Okay. All right. Okay, the reaction between SO2 and O2 to form SO3, the reaction is exothermic. Please, if they ever go out of their way to tell you that, that's probably important. Like as I'm reading it, I underline it. And it may not come up, but I feel like it almost always does. The reaction is slow at 25 degrees. However, a catalyst will cause the reaction to proceed faster. E, use the axis provided below. Draw the complete potential energy diagram for both the catalyzed and uncatalyzed reaction. Clearly label the curve that represents a catalyzed reaction. Woo! Wow, it's a lot. Okay, first, some of you just might not draw the right diagram in general. When it talks about potentials, think about like you start here, you end here, you start here, you end here. So you need to make some sort of a hump or something like that. So maybe you didn't do this, maybe you did. It needs to look something like this or something like this. First, let's talk about that. Is it my, shoot, I should have done different colors. Is it blue or green? And if you didn't, I want to draw on that. That's fine. That's also why I'm going through this. Let's talk about, there's a right and a wrong answer. Why Seth? Why blue? Yeah, it's exothermic. So I have, this is, I mean, these are my reactants. These are my products. Look who showed up tonight. I'm releasing more energy than I started with. Please find some other way. I don't think it told you. So maybe dotted lines or something, or you make an arrow. What is the catalyzed now? You have to do catalyzed? Draw the catalyzed reaction. Now you're like, well, why wasn't this a catalyzed? Could be. Doesn't really matter. We don't have values. But what would the catalyzed one look like? Less of a hump. So do I start at the same spot?
Yes.
Okay, so there are some of these where we don't start or end at the same spots, but a catalyzed reaction is simply speeding it up. And what does catalyst do? It lowers the, what is this thing called? Activation energy. It lowers that hump. But you have to start and end at the same spot. So you could label it, say catalyzed, something like that. You don't have to say try catalyzed and uncatalyzed because you were labeling one. 1 point is earned for an uncatalyzed reaction that shows that the overall exo, showing that you have an exo reaction. Okay? 1 point is earned for the catalyzed reaction curve, labeled and must begin and end at the same energies versus the uncatalyzed. So the catalyzed is a lower activation energy, but starts and ends at the same spots. And they clearly say that. Lastly, F. Predict how the ratio of equilibrium pressures would change when the temperature of the uncatalyzed reaction is increased. Ratio questions I don't love, but you have to answer it in terms of the ratio they give you. Okay? So, if I look, just hold on. Careful. Whenever you talk about increasing temperatures and things like that, and they've told you something that is exo or indo, you have to understand how that's going to interact. You can't just simply go, oh, it moves to the right. So this is exothermic. So our little trick, I have to put E on the right side. Okay? And now it says, simply put, how would the ratio change when the temperature of the uncatalyzed, so don't worry about that, is increased. So if I increase temperature, it will go to the left.
Yes.
So you just have to look at this ratio. What's going to happen to my ratio? It's going to get larger because this is going to get bigger, right? This is going to get smaller. This is going to get bigger. This is going to get smaller. If you ever need to have an explanation, you simply have to say, by increasing the temperature, it will drive it to the left because it's an exothermic reaction. You don't need to start explaining that you put an E there or anything else. You just say, hey, this is the way it went because it is blank. Okay, so if it was an endothermic reaction, by increasing the temperature in an endothermic reaction, it will drive it to the right, producing more SO3 and less SO2, if that was the case. So the ratio would increase as the temperature increases because the reaction is exothermic. The temperature raised, because the temperature is raised, the reaction shifts to the left. Done. That's what they said, which is what I just kind of said. So slow down though. Make sure you're understanding the ratio they give you. If you're like, well, I don't get why they did that ratio. It's whatever they chose to do. Is there one more? Is there a G? Did I cut it off completely?
Yes.
That is awesome. Okay, it said, how would the presence of a catalyst affect the change in the ratio? How would a catalyst, sorry, I thought I cut something off and then I looked, I cut it off so cleanly I couldn't find it. How would it affect it? It would get to that point of equilibrium faster, right? But it would not actually change the value of it. And that would be it. So, and sorry I did cut that off. That's a good question to have, just to kind of finish that up. Okay? You guys are doing great. I know we've been doing a lot. But that's problem number 2. What we're going to do, we're going to do one more multi-choice. I'm going to hit one more problem, then we're going to take a break. We'll do a couple more, and we're going to go back and forth, just kind of keep it lively. So, we're going to do another multi-choice. I'll tell you now, you're going to get done with this one early. Probably, because there's not a lot of well, this one actually has more calculations, but the non-calculation ones are faster. It's kind of funny. So it has more calculations and faster problems. So again, I'm going to give you 7, but if you feel like you're done, I will end it early if I can tell, but I don't want you to feel like you can't use the whole time. Okay, so no calculator. You can do the best you can. All right, you ready? Just this side. So you're on the right side of the first page. Go for it. Good luck. And write on your sheets, make notes, make hand scratching, whatever you need. Okay, reminder. You you don't get a calculator, so they know that some of these calculations you can try to figure out an answer almost by taking a little bit of common sense. This first one, if you didn't realize that, you aren't going to get this right. It said unbalanced, and that's really rare. So you should have had this. So I just wrote right on there, right above it. So the minute I have that, it says 1 mole of solid aluminum. So I just do the aluminum, and then I need hydrogen. So it's literally this. Because of the 3 and the 2, it says unbalanced. So I just underlined it. So that's why that's the answer. So if you did not get that, it's because you didn't balance it. And you probably just picked A. And it's B. So, again, if something's that easy, you might want to just, okay, wait, was it that easy? For most of you, again, you have plenty of time to look back through things. 28, a mixture of nitrogen, helium, and argon gases exerts a pressure of 288. If the partial pressures of helium and argon are each 37, what is the partial pressure of N2? So, mentally, I literally would write this. And you can just look. I mean, what's the closest answer to that? D? I mean, that's the closest answer. I don't need to be sitting there. Is it exactly 214? What's the next option? It's 114. It's not even close to that, right? I mean, so, again, think about that. Like, they're not trying, these are not mathematical challenges for you. They're not trying to do that. 29, could have been a little confusing. It says, which of the following statements best describes the reactivities of copper and zinc shown in the equations? Remember, the reactivity is when it's a solid, you guys. So, for example, aqueous zinc is more reactive than aqueous copper. I don't, like for letter B, that's not what reactivities are about. It's not the aqueous, it's not the metals. Copper metal is more likely to lose 2 electrons than zinc. Well, the copper is by itself, so it said it couldn't react. So clearly all of these are talking about giving up electrons. Well, that's still if it's going to react. And this says copper metal is easily oxidized by aqueous zinc. Copper metal is easily oxidized by aqueous zinc. No, it's not. It's the same statement. So it's got to be letter A. Zinc metal is more likely to give up 2 electrons. Why? Because the second equation actually occurred. And I know it was in a weird context. Like, wait a minute, why don't they just say, will it react or not? It's giving up electrons, a redox is occurring. Okay? 30, I hope you got this. Which of the following molecules contains sp2 hybridized carbon atoms? So that's 3 clouds total. Should have been this one. I just want to show it to you. All the other ones have more bonds than that. Okay, and if they ask me a question like that, I'm going to start drawing it out. Remember, carbons don't have lone pairs on them. They just don't if they're centered around things. So like this one would have a triple, it'd have to have a triple bond. So that would only be an sp. And this would be an sp3. And this is just a weird something or not. Well, no, that's an sp3 as well. Sorry, I thought it had 4 H's. 31, my gosh. It's either you kind of know it or you don't. So if you just look at the periodic table, it ends at a 3. It's in 3D. And there's no such thing as a 1D. So actually both these are gone. And that's one below it. That would be cadmium. The one below that. Remember, the D's are one behind. So unfortunately you have that or you didn't. Little math quickly here. You got units. This is how I did it. Units always help me. I have that, and then it wants to know what is the mass. Well, if I get rid of volume, I have the mass. So if I just multiply this by, whoops. Hey, look at that. That's a really nice number. Whoa. Oh, tricky. Letter D, you go too fast. Again, easy math. I'm not saying that if you don't get it, that it's difficult or hard, but it's supposed to be pretty easy math. Last one. What is the approximate ratio of those two for the acetic acid if pKa equals 4.8 at pH of 4.8? We learn about the Henderson-Hasselbalch equation. So if you have this, I'm just going to write this down once. A lot of people don't do Henderson-Hasselbalch because they got rid of it like 2 years ago. They're like, let's not do it anymore. And everybody's like, what? It's such a good equation. If the ratio for this to equal these, wait, hold on. If the pH is 4.8 and the pKa is 4.8, that means they equal each other, right? So what must this be? It has to be a 1-to-1 because it has to get rid of that. I guess to me, you guys, if I look at all that, I'd be like, how would I know if it's a 2 or 1? 2 over 1. Like, I don't have a calculator. Like, and I got to take log of 1 or anti-log. Like, that's actually a little dirty too, log 1, because be like, oh, it's a 1 to 1. It's log 1. That's not the question. It's asking the ratio. So actually, I do think that that's a little tricky. So again, just good to see. We're gonna do one more problem, then we're gonna take a break. Take a break. But we're gonna, not yet. We're gonna do one more problem. Then we're gonna take a break. I don't even think I said that incorrectly at all. See you, Mason.
He's coming back. He's
Oh, yeah.
coming back.
He showed up late. He needs to leave. An external direct. Okay, this is a little different. I wanted to bring this one out. It's older, but in case this comes up. An external direct current power supply. So notice, it's not voltage. Is connected to 2 platinum electrodes immersed in a beaker containing those copper sulfate, so it's in the same solution. As the cell operates, copper metal is deposited onto one electrode, and oxygen is produced on the other. So that's what the bubbles are. Okay. Cell operates, I already said that. The 2 reduction half reactions for the overall reaction that occurs in the cell are shown in the table below. So to give this to me, as confusing as maybe and as foreign as this might seem, we're able to do almost all this, even though these do evolve as we go. On the diagram, indicate the direction of the electron flow in the wire. Okay, so what you have to understand is how we interpret this still. Okay, so if it's being plated, right? It's being plated. Okay, so that means electrons are going to it or from it. Think about it, there's Cu2 plus in here. To be plated, it has to go onto it, right? That means that that electrode has to start getting overloaded with negatives so that 2 plus goes onto it. So that means electrons have to be flowing that way. Does that make sense? Like, no, well, wait, this is a power voltage versus a voltmeter. I don't understand any longer. That doesn't matter. Whoever's gaining mass has to be gaining the electrons because that's from the solution, the ions have to go onto the electrode. Okay? So that's what you draw for that first part. So it's going counterclockwise. Okay? B, write a balanced net ionic equation for the electrolysis reaction that occurs in the cell. Whoa! Don't understand these terms. It's from my given equations. Okay? So I just have to make sure that my equation that I understand, which is the copper one, is correct. So the way that it's given to me, is this bottom one correct in how it's happening? Okay, and I know because it's making solid copper, right? So what do I always have to do? I have to have electrons on one side and on the other. So I always have to flip one. Now you're going to notice something that's about to happen, and we'll talk about this. But this one has to flip. So by doing that, please add these up. What always has to be equal? The electrons itself, right? So if you have to double one of them, it's not asking for any voltages yet. If you have to double it or cut it in half or whatever else, please do so. What is the overall net ionic equation? But you didn't have to come up with that from scratch whatsoever. And so far, even though it's like, whoa, this is a foreign problem, we've never really done it this way, you should be able to handle it if you just slow down and think about what you're given. I had faith. Some people thought you were deep. Oh, you're coming back in the morning.
It's the biggest
So you have to, can't you have the first
6
one
years.
instead of double?
Yes.
the second?
You could have, I guess.
So they're both right? Or,
Yeah, I mean, I didn't think of it that way. We usually bring it up, not put it down. 1 point is earned for having all 3 products. So by the fact that they have to find a way to grade it sometimes. So did you just realize that you flipped it? So basically they're realizing if you didn't balance it correctly, and then 1 point is earned for balancing. So Ashley's question, very good one. What if you realize, well, I want to cut this in half? Perfectly fine, you balanced it. Okay? So that's 2 points. 1 point for flipping it and 1 point for having it all balanced. Letter C. Okay, now, here we go. Let's see if you can interpret this. It says, predict the algebraic sign of change in G for the reaction. Justify your prediction. And hear what someone has to say about this. Tyler, louder, go. Okay, let's use, you're right, but let's use something else that we know. You're right. Nothing that you said was wrong. What else? Why else do we know it's positive? Noah? Because? Okay, so good. But what else have we given? What? There's an overall negative voltage because now you have negative 1.23 plus a positive 3.4. So the result is a negative voltage. Does that make sense? Like that's how we always know if a cell is working or not. You're right. You see a power source, it's definitely forcing it the wrong way. And it's moving the opposite way of what nature would allow. But it's an abomination. But because it has a negative voltage, please be careful. We have to understand that a negative change in G is spontaneous. And my gosh, there's a lot of stuff working in our heads. But you'd have positive G, I would say, because you have a negative voltage. It's not spontaneous. Okay, I will say what they have. The sign of change G would be positive because the reaction is not, that's all they wrote. Because the reaction is not spontaneous. That's all they have. I just want to feel, because it has a negative voltage, done. There you go. Math. Calculate the value of change in G for the reaction. Now this is where I always hesitate because times have changed. Thank goodness, not enough. Okay, all right. We're okay. So find your orange sheet, go to page 4, which is where the electrochem part is. I want you to try to, so we need this, okay? Don't just think you have to solve it from scratch. Can you look, see how after the ones with the big sum E signs, right? There are 3 equations that say change in G equals, and then equals, and then equals. See that? They really probably should write change in G each time. I feel like, it's like, ink, I tell you. So all those equal change in G, which one would be useful? The last one. That E is voltage. That E is the energy of a cell. Okay? So we need this equation. Okay? So let's just talk about what we're using there. So what's the N? Number of moles of electrons. So I have 4 electrons, which is technically moles. That's 4 moles of electrons. Okay? Then F. Oh, I don't know F. It's on the right. Faraday's constant. It's on the right, though. That has nothing to do with memorization. It's fact. Now, usually they write it as 96.5. Just FYI. If you want to write it fully, like on the test, I would just write what they give me. But it's coulombs per mole, I believe. Am I wrong? Is that right? Okay. Yes, no. And then my overall, if I add this up, I think that's negative 0.89 volts. When you're all said and done, it doesn't really ask for units, but it's G's is always kilojoules per mole. Just know that. So this is plug and chug, unfortunately, but it's just, do you recognize that that's what you should be using in that? So you could have 2 different answers. In fact, actually, does this actually give you 340,000?
Yes.
Okay. If you get that, because you're just staring at this, there are hidden units in here with coulombs and voltages. If you got that much, do you think that's a kilojoule or a joule? Probably a joule. Right? It just is. Our experiences, we don't have that many kilojoules. Okay? So that would be that many moles. Now, technically, it just asks for the value. So those of you that are always constantly trying to kind of push the envelope, like I'm going to give them just the amount that they are asking for, it doesn't ask for a unit. So if you didn't want to write the unit because you're unsure, just double check the question, and you might be able to get the right. 2 points. 1 point earned for. Unbelievable. 1 point earned for getting that. Usually it's that, actually. Like if you understand that it's moles. Math. Math. E. All right, this one's not that hard. At least one of the points. But you got to know what you're looking for, so I'm going to help you out right now. It says, an electric current. You can make this difficult, or you can just realize that your orange sheet helps you out a lot. You have 1.50 amps, and it goes through in 40 minutes. It says, calculate the mass in grams of Cu deposited. Okay. And if you're like, whoa, what am I doing? Okay, if you're given amps in minutes, which is time, so this is time, we know what an amp is. And we're going to make sure that we would recognize this. That's a current. So if you find that there's this. You see that under electrochem? Again, sit in electrochem and be like, okay, I'm supposed to sell for something. What the heck? Well, plug this in once. What do you think the time's always in? Does it even say? Maybe it says. Oh, it says it even. It says time seconds. So it's, oh, okay. So what I need to do is this. What I would do is, you could do a T-chart, I guess. Oh, I can do this. This won't make or break you, but you should at least recognize at some point, like, I don't know what I'm doing. Okay, fine, shoot. Okay, those amps, it's a current, or the time, and this other thing, oh, it's the I equals Q over T. We haven't done that in a real long time. That's why I wanted to make sure we did that. So, if now you're stuck, because it's asking for mass, this is why we need to see it again. We haven't done this in a long time. What am I supposed to do with this? Just write it out and see how you could potentially change this. If you look, I'm just looking at my orange sheet. Is there a ratio that uses coulombs? What does it say?
1 volt equals 1 joule.
True, but there's another ratio that actually has coulombs just in it. That's right. It says coulombs per mole of electrons. See that, the one above it? Oh my god, I just spaced up. 96.5. It's per 1 mole. It's per 1 mole. Okay, if this comes up, this will come up once, and that's it. It's asking for copper specifically. So let me try to help you with that. It's going to be a mole of copper per mole of electron, not the entire equation. So if I have 1 mole of copper, how many electrons come off of it? Dos. Look at the equation. It's right there. And now, at this point, if you visually just see this in a recent amount of time, which is tonight, usually you have at least a shot at this again. I can get from moles to grams. I'll calculate it for you because I want to move on. So if you did not get this all right, if you got Q at least, that's a point. And then the other point is for the final answer. So it's 2 points total if else, and you just got 1.19. But there are other ways to do this. They did it in a very different way, like at least in the beginning. They did it more in a T-chart fashion. But this equation is what's been given. They used to not give this equation. They used to make you actually know that an amp is a coulomb second. And they made you had to know. It's not good. Finally, F. So you're on this test, and that problem just, let's say, it hurt you. You didn't do well. It doesn't mean you can't fix it. And the next one, it might be totally unrelated. Calculate the dry volume, so you don't have to worry about all the solution. So it's a gas. In liters measured at 25 degrees, 1.16 ATMs of the oxygen that is produced. Okay. It's ideal gas law. Here's the problem. It's of oxygen. We haven't talked about oxygen yet. So if you're looking at your equation, way back here, we know copper, you have to find oxygen. So you take what you had before, this is the one issue, okay? And now you gotta go through it. You got to find how many moles. Oops. My initial equation was 1 over 2. So I'll get those moles, and then I just plug it in. So if you botched it, please write assumed moles of oxygen or this, or something. You can probably get the point at least for the ideal gas law part, or placing it in the ideal gas law. At least you have a shot at that. It says 1 point is earned for calculating V consistent to previous calculations. So whatever you had, as long as you're calculating it correctly. But if you blindly put in copper, that could be a problem. You had to realize, okay, wait, I got to do it a gas. Gas law, gas substance. You can't solve for a gas, or with a gas law, solving for a solid. Okay? So that was a longer one. Like our next one's much shorter, so it shouldn't take as much time, I hope. We'll see. We're going to take a little bit of a break. I know we're getting down to it already here. So the answer, by the way, 0.197 liters. Again, 2 points. 1 point earned for the moles. 1 point earned for the energy. So please get up at least. All right, so you got two reactions. You have H's and S's on both. It says A, is reaction X represented above spontaneous under standard conditions? Justify your answer with a calculation. So let's just kind of do this together a little bit. What am I probably utilizing? Change in G equals change in H minus T change in S. Oh, I don't remember that. It's on your orange sheet. You can definitely, if you're given an H and an S, utilize it. The big thing for this, units. Okay? Your S is almost always in joules, and your H will almost always be in kilojoules. It's just the way it is. So you better make sure that you use it correctly. So I have, I'm going to make it larger. It doesn't matter which way you go with it. Is that 298? Stated right there for sure. So the calculations were the point, and then your justifications are the point. So it's negative 5,000, so it is spontaneous because G is negative. And that's the question that, or the answer that you should be saying. So it is spontaneous because change in G is negative. That's all my answer right there. 2 points. Okay, then you get to B, and a lot of people start to freak out because you just aren't thinking about what you're kind of working on. It says calculate the value of the equilibrium constant, so it says KEQ for the reaction X. So you could look at this and go, oh, I'm going to put them products over reactants. Problem is I don't have any of those values. So think about it. Think maybe my orange sheet can help. And if I look at my orange sheet, there is an equation. It says change in G equals negative RT natural log. Okay. So I just have to plug that in. Again, using that. So I just used a G. Now, you gotta be a little careful. Your R values on your sheet, you have two of them, 0.0821 and 8.314, and the 8.314 has joules in it. So you want to make sure you use the proper one, meaning like units. I'm really, oh boy. I would like to see if you actually get this right. Calculation-wise, that can give you a bit of a challenge. Solve for it all, get it to the other side, and take e to the answer, right? Second natural log for most calculators. See if you get what I have. This is only worth 1 point, but can you get that? E to the whatever value all those equal. Something around 7.531. Technically 8 because if I didn't put a decimal after my negative 5,000, it's 1 sig fig. Probably not a problem you're caring about too much. Okay, that's only 1 point though. C. Explain, or what effect will an increase in temp have on the equilibrium constant for reaction X? Now, it says explain your answer. It does not say in terms of a calculation. There is a calculation that you could apply to this. What do I mean by that? If you increase the temp, what could you do with the previous problem? Couldn't you put a larger temp? You could, right? So if you ever get stuck and you're like, well, I use an equation, or I know what equation I would use to solve it if they gave it to me, use the equation, and you could actually say, according to the following equation, if I increase the temperature, blank occurs. It works. But we don't have to, I want to do a different way, because I think this is more important to notice. Which one is about heat and heat flow and temperature? It's that, right? So what does that mean? Where would my energy be on my reaction? It'd be an endothermic, so I would have plus E on this side. Okay? I think this is a better way of understanding this in general. So if I increase the temperature, it's going to drive the reaction to the right. What does that do to a K? I'd have more products, right? And smaller reactants. So it'd be a larger K. So what you could say is because it's endothermic, increasing the temperature drives it to the right, producing more products, which would cause a larger K. You don't have to break it down, which would cause a larger numerator and a smaller denominator, which then results in a larger number and a ratio, and they get it. They're all chemistry teachers. We hope. Some guys off the street, we needed one more. Using crayons from Perkins to grade it.
5.
Oh, this kid got a 7 on his final score.
7 to 5. That's cool.
Letter D. You started a junior. D. Explain why the standard entropy change is greater for reaction Y than reaction X. Anybody want to, it takes about 1 sentence, maybe 2. Why is there a greater change in entropy in Y than X? That is great, and then I would just follow up with some sort of thing like, which means that in reaction Y we gained, there was a greater change in disorder, or something like that. You're perfect though. Whenever it talks about entropy, increasing or decreasing, either you look, first off, this is what I look for first. Which one has more or less gas on which side? So if they both have gas, then it's literally about a numbers game. Otherwise, it's also about states. So yeah, we have some disorder, and then we don't have any more solids, so we've gained some disorder because of that. But here you went from order to purely disorder. So that is the reason. Let me read what they have. They have a really long paragraph. You know these by now. It's like, whoa, that's really deep. Both reaction X and Y have solid iodine as reactant, but the second reaction in reaction X is chlorine gas, whereas the second reactant in reaction Y is liquid bromine. Liquids have lower entropies than gases, thus in reaction Y, I regret reading this, the reactants are more ordered and have lower entropies than in reaction X. The products of both reaction X and reaction Y have about the same disorder, so the change in entropy from reactants to products is greater in reaction Y than in reaction X. Sorry, once I started, I didn't think I should stop. I've gained more disorder by going from a liquid to from a solid and liquid to a gas than going from a solid and a gas to just a gas. I've gained more overall disorder. Whew. Finish this up. Letter E. Above what temperature will the value of the equilibrium constant for reaction Y be greater than 1? Justify your answer. Okay. Above what temperature will the value of the equilibrium constant for reaction Y be greater than 1? Justify your answer. So you want, okay, talking K, okay, you're given H and S. They want a value, okay? So if you have H and S and they want a temperature, then, I'm trying to think of some other things here. Anybody know? Okay, so this is the key number. I was going to use a different equation. I was going to use this one. But that's not using any H or S, and then you're looking for temperature still. What's going on at 1 when K equals 1 exactly? And now anything can be equilibrium, but you literally are equal, right? You have the same amount of products and of reactants. Like you don't have more of one or the other. When you don't have more of one or the other, you're not shifting one way or the other. Meaning, right, or you've reached equilibrium, but that means it's not going this way at all or that way. So it's not spontaneous either way. So this is, if you didn't get this, you wouldn't get this point. This signifies that change in G is 0. Here's my hint to you. If you're ever doing a problem and you're like, man, I have some of these, I just feel like I'm short one. Like I don't quite have everything. G is probably 0. That's probably what it is. Phase changes. Phase changes are G equals 0 because we're not actually. It's that the heat the heating curve where it's flat at that point. We're not gaining and losing heat. It's all going into changing your phase by overcoming those IMFs only, not by heating up the molecules. So if I did that, FYI, this would be 0, and then which one? I'm sorry, I'm slowing down here. Is it a reaction Y? So then I have to plug these in, and I do have to plug them in. It says at what temp? So that's what I'm solving for. It's a subtraction. So you'd solve for T. I'm going to do it for you right now. The big trick for that one is realizing, okay, G is 0. And if you're like, I don't think I get that one. Okay, fine. But at least you've heard it once. Maybe you will. Maybe you won't. When I look at a problem like that, be totally upfront sometimes. I'm like, wow, is that change in G for 0? Like I'm missing something. At least know that that's an option. G has to be 0 then. I'm at equilibrium. If you're at equilibrium, you're not spontaneous anymore. Nothing's being you're not. It's not going forward. It's not going back. So E. You get an answer of this. The problem is, it says above what temperature? So above what temperature? So that means ultimately you have to say, that. One point is earned for the fact that you said change in G is 0. So they're testing you on that, and then 1 point is earned for the correct temp. Last one. For the vaporization of solid iodine, the value of change in H is 62. Using this information, calculate the value of change in H for this. Where is this equation in this problem? The answer is nowhere. Parts of it are up here, parts of it are right here. If you feel like, man, it's kind of like that one, that's close. They're asking for change of H, that's close. Then this is a Hess's law. It gets you every time. You just have to take this equation and use one of these equations, and we just have to recreate this one. So which one do we want? X, right? We want X because of the CLs? Yeah. So let's take a look. Let's add them up. If you flip and do all the things you're supposed to do, By doing that, I flip this one. I will get this equation. And I had to double this. Right? So I doubled reaction X because I need to get that to equal that exactly. So I doubled it, so it's 2 times 18, and then I flipped the sign of that one. You're going to get 2 points. 1 point is earned for getting the change of H of either. Oh, jeez. If you doubled that or took the negative of that, you get a point. That's generous. Either one, and then you get 1 point for the actual answer. Okay? So, continually remember that. If you're talking about H's at some point and then it asks find a new H for a new equation, be like, man, that's close, but there's some of that in there, but it's not all in there. Okay, there's got to be one somewhere else. That's probably Hess's law. I know we're doing a lot, but in my opinion, after this, you should just go veg for an hour or so, a couple hours, and then go to bed. You don't need the review. Okay, I don't know what that means, but people are just saying random words to me. Math, okay, we're gonna do this again. So you should be on the back side. 1, 2, 3, 4, 5, 6, 7 of them. I'm going to give you 7 minutes. You just write right on there.
No.
What?
Are we on the 30?
I got it covered.
Did I mess this up?
Yes.
It's fine. Okay. So, 1, 2, 3, 4, 5, 6. There's 7 of them. I'm going to give you 7 minutes. No calculator. You ready? Good luck. Give it a shot. 1 minute. Okay, take a look at these. Number 34, you have a Ka of HCl, and it has, that's the K, you got a pH, and what additional information do you know about the concentration of its conjugate base? Well, to be able to figure out anything in any problem, you need to know how much you have initially of that acid. So you need to know the acid, and that was confusing based on the options. So if you didn't get that one right, that you probably were going around and around and around. But you need to know the beginning. Whenever we did an icebox, you always know the upper left. I guess that's how I can rationalize that, okay? Number 35, this one's confusing when it keeps talking about electrons being moved, but this is what I did, like actual, like real time. I looked at this problem, it says it's spontaneous, that's important, it means it's moving to the right, which the following statement is correct. It says Cl is oxidized by Br, and I'm like, okay, wait, is it? So that's a 0, oh, that's -1. That's not oxidized, that's being reduced. So that can't be. And right there, then my mind kind of got, was kind of good. I started understanding, okay, so I'm tracking these electrons. Br2 is more reactive than Cl2. That's not the case. It's going this direction. It's spontaneous. It's happening. So that can't be it. Cl2 gains electrons more easily than Br2. It went from 0 to -1. I'm feeling pretty good about that. Br is easier to reduce than Cl2. Again, it's going this way. So it can't, they both can't reduce. This one's the one that's being reduced.
Let's go.
So it's letter C. Number 36, this one. I love it when answers are all positive and one's negative. It says calculate the standard enthalpy. As long as you understand what you're doing, it's products minus reactants. Notice it says standard state. That means this one's 0. So just make sure you're doing the proper numbers. There's negative 396 minus negative 297, and you should just be able to eye that up. Oh, it's still going to be negative. Okay? As long as you didn't do the positive 99, you were fine. Upper right, 37. Calculate the change in G. It gives you formations. Guys, if it gives you formations and it gives you all the same, just like the last one, all H's, this one gives you all G's, it's still products minus reactants. So in this case, I took negative 237.1 and subtracted negative 58.54. Again, an answer should be sitting there. Again, it's just about estimating. Okay? My favorite one on here. Calculate change of S for the reaction, and they give you these. So you're thinking, okay, I can do this, I can do this, I know I can do this. And you start putting your joules and your kilojoules and all that stuff, and you can get the answer. Thing is, they know you don't have a calculator. I have 3 moles of gas to 2 moles. What's happening to my S? It's going down. It's the only negative number. Boom. I didn't do a single calculation. When I see, guys, little big hint. If you look and you have to do calculations, look at the options. And if they may not do this, and if I was a test creator, I wouldn't. But if they're all positive and one negative or vice versa, just know that and then think, does that help me at all? They know you don't have a calculator. Which one's fusion? Fusion's fusing things together, so you should be putting things together. So what is the only one that's actually adding them up? D. 1 plus 3 is 4. That's fusion. The other ones are splitting. You're like, I don't get it. You split it. You made smaller atoms or isotopes. And then finally, number 40. This is all I did for this. Is I have a 30-gram sample, and I want to know how many moles of H2. So this is stoic. But be smart about it. So this is what I wrote. Like, this is all I wrote. 1 to 1. So that's a little less than 50%, right? It's a little less than 0.5. You know what I mean? Like 30 over 60 would be 0.5. So it's a little less than that, so it's 0.46. Okay, let's go. Next problem. And I appreciate that we're not trying to rush. Oh gosh, where am I? Okay. Okay, here we go. A 0.150 gram sample of solid lead-2 nitrate is added to 125 mils of 0.1 molar sodium iodide. Assume no change in volume, chemical reaction takes place. So there I am. Even tells you that's my solid. List an appropriate observation that provides evidence of a chemical reaction from the two compounds. What are you going to actually notice? There's only 4 things you can always notice about a reaction. So what are you going to see? And I should have underlined that. It's honestly, it's a double, but that's not what I observe. I observe a precipitate, right? I'm going to observe a precipitate. If you feel like you need to say more, you're going to observe a solid that comes out of the solution. You don't need to say the color. Precipitate forms with an appearance that is different from that of the dissolving solids. Like a solid will appear, or there'll be a new compound that shows up as a precipitate. Okay, that's one point. Letter B, calculate the number of moles of each reactant. Sounds like they're setting me up for a little bit of limiting reactant strike. So, this is pretty classic. And in the way I'm saying it is that one they give you in grams, the other one they give you as a solution. So I have to do 2 different ways of doing this. So because of time, I'm going to kind of guide us. I think we would be able to get to both these, but let's visually see this. So this one I need to do a T-chart, right? I got to go from grams to moles. So I will get you your molar mass. Very small. What's the other one? I have molarity and I have volume. So I can get moles that way. How I'm going to do that, I'll do it over here. So I'm going to use these 2 numbers. I'll do it up here. I like to set it up, and if you want to do it in a different way, that's fine. Like the equation would be. It's the way I was taught, so then I never make a mistake in multiplying or dividing. Like it's just clean, right? So I'm going to do it the way they have it just so I don't mess this up later. Right, it just shifts it over one more. I'm multiplying by 0.1. So let's be real clear, though. This is of NaI, and this is of PbNO3. C. So 2 real standard ways of finding moles. C, identify the limiting reactant. Show the calculations to support. Okay. When you are comparing something to something else, you use mole ratios. You compare it in moles. They already made us have it in moles. Does anybody know which one is going to run out just based on the sheer
Definitely
PbNO3? Okay, so let's use the other one. If you use the other one, hint, if you, let's see if you're right. You compare one with the other. So for every 2 moles of NaI, I have 1 mole of PbNO3 2, right? I'm actually curious if that's what they did too. No, they did it the other way. So I cut that in half. Oh my God. Yeah, that's fine. No. Do you have enough? That's how much I need. I don't have enough. I only have that much. That if you would have done the other one, it would have said how much NaI you need, and it would have been not as much as that number. Okay? So you have to state it then. PbNO3 is the limiting reactant. One point is earned for the identification, 1 point is earned for using some sort of mole ratio. I don't mean to be going too fast with this, just the beginning parts I just stoic and relating it to each other. But now, here we go. There's only 2 letters left in this one. Calculate the molar concentration of NO3 in the mixture after the reaction is completed. Okay. So, do you understand what we're doing with that? So you have this many moles, and this is the problem. that is saying how much extra I have. Or this is how many moles I have of it, I'm sorry. What is NO3? NO3 is a spectator, correct? That means it doesn't get consumed. So however much you have in the beginning is how much you have at the end. You have to make sure you understand. I have this. Let's see if someone can tell me and shed some light on this for me. Is that right? Divide by 2?
Yeah.
Every ion carries a certain number of moles. So this breaks off like this, and like this. Each of those has the same amount of moles. So I have double those moles. That's what this problem's testing you on. You have twice the amount. Every molarity or moles, you have double or it relates to the entire compound, and then the number of ions that come off of it all carry that molarity or moles. Make sense? So I get that value, and then what do? This isn't all that complicated. I take that, and what am I going to divide it over? I want molarity. That's the volume. Like, but wait, that didn't have a volume there. I dissolved that solid into this solution, and it said, assume no change in volume. So that's my volume. So all I do is that. So what they're testing you on, did you put the moles over the volume, or did you do double the moles over the volume? That's what this one's about. One point is earned for correctly understanding that you had to double that. And then 1 point is earned for the answer. So, to the last one, which is why I picked this question. They like to do diagrams, and in general, we're not as good about that. And not you, just all high school chem students have a hard time visualizing this. Circle the diagram below that best represents the results after the mixture reacts as completely as possible. Explain the reasoning used in making your choice. Okay, I don't want to hear a total answer here. Can anybody tell me the one I can cross out right away?
No precipitate.
Okay. See, it's all about getting your options down. Is there any other one I can get rid of right away? Tyler? Yeah, because that's not the precipitate, right? So now I'm down to 3. What I'd like you to do, take a moment. If you want to talk to somebody else, this is not as easy as it looks. I want you to try to figure out which one is the right answer. So think about it. Think about the ions that should be present. Think about in the amount that they're present. Are you worried about the size of those circles? They're not, no. They're just trying to show you, remember, negative ions are bigger, positive ions are smaller because positive has less electrons. Take a shot at least. If you don't want to do an explanation, fine, but you got a 33% chance. So right there, first, always, get rid of things that don't make sense. They're not all going to have ones that all make sense. There's a few that are going to be throwaways. Can you tell me, is there one more that I can get rid of? Tyler? Lower left, middle, or right? Let's say that. Has I remaining in the solution? Maybe. Why that one, for sure? Okay, and I'm not saying you're wrong necessarily, Tyler, but there's one, like, this is from the limiting reactant, and it all precipitated. So there cannot be any PB in there. Trying to show you how you could get to. Now, if you're stuck, now you just take a shot. So what's the difference? Clearly I, right? It has an iodine in there. Can you tell me, iodine results from what? The limiting or the excess reactant? It's from the excess. So the reason why you pick the upper right is because there should be some remaining iodine. Yeah, but that all precipitated. It came from the excess reactant, so there should be some iodine. So whenever you do one of these, and this has come up before, there really should be 3 different ions. Okay, the 2 from the ions that are not part of the precipitate, and then the 1 from the precipitate that resulted from the excess. Does that make sense? That's because of that? So you get 2 points, one for just finding the right answer and then explaining. Okay. This is how this is going to go. We have one more multiple choice. If you feel like you cannot handle going through the last, I have a kinetics problem after the multiple choice when you go over it. Like you said 615.
totally fine.
I am going to go through one more problem though, and it's a short kinetics one, and we haven't done a pure kinetics one yet. But we are going to finish on the time of 6:15. But I'm gonna stay here and keep going, even if no one's here. I'm teaching it to an empty room. I'm not kidding, because I want to record it just in case someone is waiting and still see it. So that's dedication. So we're going to go to the last set. We crossed out 54, correct? So there's 7. Okay, no calculator. All right. You ready? Know what you're going to do from up there? Or you? Okay. Here we go. So last set of multiple choice. Give it a shot. Do the best you can. Keep the focus. You guys are doing great. Okay. Good luck. I'm going to cut this one off 1 minute early because there's not a lot of calculations. So just FYI, you'll be fine. take a look quick. It says it takes 2.4 moles. You have a sample. It decays to 0.3 moles if the half-life is 1 minute. How long does it take? So this is what I did. I have 2.4, and then I just, what is a half-life? It's the amount of time it takes for you to lose half of it. So then I just put 1.2, and then I put half of that, and then I put half of that. So if I start at 0, this will take 1 minute, another minute, another minute. That's how that works. You start at 0. It takes a minute every single time you lose half. Letter B, which of the following is true about a catalyst? If you can just find it, I don't have time to really talk about each one, but it lowers the activation energy. If you can just leave remembering that always, it always lowers the activation energy. So if I drew something like this, if it all of a sudden went lower, it lowers the activation energy, right? Letter number 50, which of the following is the weakest type? What is that? Which one? Because it doesn't say the actual name. Right. I know it doesn't say London. An induced dipole is a London force. Okay, the other one's dipole. Dipole, ion dipole, what's that? It's an ion to a dipole, so like a water to an ionic charge. Oh, I hope you got this all right because we just talked about it. If G equals 0, it's in equilibrium. 52, how many moles? This you have to actually do. So if I do this really quickly, combustion makes carbon dioxide and H2O. You had to balance it. Probably took you a little while, and unfortunately it was pretty big. It did this. It was 18. So if I just did 1 mole of octane, and I wanted how many moles of H2O, it's 18 over 2. Right? So that's 1 times 18 divided by 2. That's 9. Because I wanted to go to water from here. 53, the actual math problem that you would need, this is M1V1 kind of thing. So if I have 12 molar, and I know what volume it is, and now I have 500 mils, and I want 2 molar, well, basically what you're doing is you're doing 1,000 over 12. Well, 1,000 over 10 is 100. So you have a little bit more of this, so the only logical answer would be 83, right? Because 1,000 over 10 would be 100. Last one, 55. The heat of solution for LiCl is negative 37.04. That means to make a solution, to dissolve it. Which of the following statements is true? If you read this, a lot of these are wrong. Like surrounding the molecule. Water doesn't surround the molecule. Water surrounds each ion separately. So it talks about that in almost every single one as a pair. But it releases heat. The negative. It releases heat. So that was A. Okay? So I'm doing one more kinetics problem. If you want to go, because you just can't handle it, that's okay. I don't mean to say it that way. But I'm going to go through it. It's probably going to take an extra 10 minutes. If you are leaving, or if you're not, I'm just going to say this now. Breakfast starts at 7. You got to be leaving this room by 7:25, and you have to go directly to your cars or your ride. Yeah, you're supposed to be there by 7:30, even though I do feel like you're just going to be waiting and sitting. We need pencil, a pen. Evelyn was nice enough to bring some black pens, so I'm going to have them here in the morning. Tomorrow, don't take them now. And you need a calculator.
Wait, where is the church? What is it?
Right down the street on St. Augustine, right across from the middle school, St. John's. Okay? All right, kinetics.
Wow, slow blow. Come on, Mason. Do it. Shows up late.
Here we go. Last problem of the night. This makes me smile, as many people want to say. So, thank you. For the gas phase reaction represented above, the following experimental data was given. A, determine the order of the reaction with respect to reaction A. Justify your answer. That means probably some sort of calculation. B, determine the order of the reaction with respect to B. Justify your answer. And C, write the rate law. I'm going to let all 3 of those happen. What are we doing in general? You need to find how the concentration affects the rate. All of you that stay, you get extra credit. What reactions am I looking for letter A? He crawls and just like sits back up. What equation am I looking for reaction in respect to reactant A? What experiments do I want? 2 and 3. I am using this one also. You cannot be so far in your head, be like, well, they changed too. This is experimental data. Okay? So that one is definitely the one I want. So I always put the larger number on top, smaller number on the bottom, and then I use the rates. And already I can see what's happening with this one. What are you using? We'll talk about that in a second. Anybody who's ahead of me or at least can look at it. For reactant B, what experiments do I want? 1 and 2. So I'll do it this way. Yeah, and again, they change, but not a lot. Okay, so I'll do that right here. Yeah. I did do 2 and 3 for the first one.
But couldn't you do it for the second one?
No, you can't, because the second one, you need it to see it change. You need to see what, by changing the concentration, what effect does it have on the rate. And it does have an effect.
Not possible.
So what is the order of the first for reactant A? 0, because I quadrupled the concentration and the rate did nothing. The rate was unaffected. This number could be anything. If the rate is 1, it's 0. So reactant A, you have a 0 order. Reactant B, what is that? It's a second order. And you're like, whoa, 4 to 16, what? It's the idea of squaring it. The order is a exponent. So if this was 2 and this was 4, that's still second order. If this was 4 and this was 8, or another 4, I mean, sorry, I quadrupled it and the rate quadrupled. But this is second. So, see if you got this right. Rate law. Last night we did a rate law twice. Do you know what that looks like when it says rate law? Because you won't be able to come up with anything. It's not anything with t's in there in time. Generically, it's always that, and it could be multiple ones, okay? It's rate equals K times the reactants. In this case, the best answer is this. You could write A with a 0, but the best answer is that, right? Because anything to the 0 is 1, so that would not affect it. By the way, all that so far is worth 1 point each, so far. Okay? But, by the way, if you messed up A and B, as long as your rate law reflects that, so if you put first order for one of them, as long as you showed it. So if it was first order, it could be K with an A, and then this with a 2. That'd be first order and second order. Okay. Okay, we're already halfway done. Now I'll go get that later. D, determine the value of the rate constant for the K reaction. Help me and include units. What do I have to do now? I plug it in from any experiment I want, right? Because now I have the rate. The rate is the final part. I have concentrations. I'm going to pick the first equation. This is just usually easier that way. I'd suggest putting units to help you. I will get you the number, but you're going to have to get your unit. I want you to give it a good shot. What do you think that looks like? Remember, the left has to equal the right. So I usually have to eliminate or get rid of something. And I also maybe have to bring something to the table. So I hope, there's 2 ways you could have written it. We'll just leave it at that. Or this. Actually, that one's probably the easiest. You got to get rid of one of your molarities, and you got to bring time into it. to make it equal molarity over time. So it's any one of those three. That's 2 points, always. One for the answer, one for the unit. Remember, it's liters over moles, one less than the overall order. So because those are ones, it's one less than 2. E, calculate the initial rate for experiment 4. So now what can I do? Because I solved for a K, I can replug it into here, right? And now I just plug that in, and now I don't know rate. This is just a step-by-step problem, initially. The final parts we have not seen in a while, so that's why it's really important that we see it again. Which I'm sure Mason and Grant will be watching online later tonight. So I just plug it in like that. So it's 3.13 times, again, if you're like, I don't understand now what to do, after you find the order, and then you find the K, you're just plugging it into a new rate law, and you can find a new rate at any time. Okay, so let's see how this all applies, and we had this question on one of the multiple choice a little bit. Following mechanism has been proposed. Okay, they have to be proposed. You're not going to come up with it from scratch. Provide 2 reasons why the mechanism is acceptable. So what's one of them? There's 2 parts.
The slow step represents the rate constant.
Good, because you have b squared, right? Okay, that's the first one, and I would actually say because there's 2 b's and it's a second order. What's the other part that's acceptable? That's step 1. The other thing still has to work. Anybody? Give you a hint. What if I do this? If I add them all up, it equals the overall equation. Right? That has to be the other part. So get the light, right? So if I cross that out, it equals the overall equation. That's how mechanisms have to work. They have to actually add up to the overall equation, and then the slow step has to reflect the rate law. Done. I don't know. Let's see points. 1 point. Ooh, for each reason. And finally, great ending. In the mechanism in part F, is species E a catalyst or an intermediate, and justify your answer? It is A or N. I don't know. A apostrophe or a parenthesis N.
Ooh, English.
What is it? It's an intermediate because, and this is all we have to say, it was a product, then a reactant. You don't need to go further. If you're struggling ever with any explanation, just say the most obvious thing that you can say. You know, with an equation, I'm starting to see what you could start doing with some of that, but give you 1 point. Thank you for staying. Mason, right? No, I appreciate it. We were a little over time, but so tomorrow, breakfast starts at 7. Please, usually people get here by about 7:05, 7:10. Then you're up, your brain's starting to work. You're not rolling in the last second asleep.